Rational and irrational numbers. How are decimals and fractions related? Well, a decimal can be represented as a fraction, and a fraction can be represented as a decimal. These are just different forms that a number can take. Now, when we look at a fraction, it's similar to something that looks like this. We have two parts and separated by a line, and we're going to talk about those parts in a second. And with a decimal, it has represented by this point in between called a decimal point, and we have numbers with place values. Let's focus on fractions first. Now, the top part of the fraction is called the numerator, and the bottom part of the fraction is called the denominator. This bar in between is used as a division sign. So when we read this, we'd say A divided by B. Now, we have in the past, when we first learned how to do division, we used long division. So we should be thinking of that as well. That way, when we go to do long division to figure out what this is turned into as a decimal, we would put the numerator inside underneath here, and the denominator would go outside, so that we would be able to change that fraction into a decimal. Now let's talk about decimals really quick and place value. We know that this is what we're normally looking at, and this is what we call the ones place. Okay, but once we start going over to the other side of the decimal, it starts changing. We have what we call the tenths place, we have the hundredths place, and we have the thousandths place. So we need to be able to read our place values, because that's going to help us in order to change the decimal into a fraction. Now, we're going to practice here taking 1/4, and we're going to start with something basic so we understand the concept. We're going to take the numerator, put it underneath, and the denominator is going to go outside. Now, when we do long division and the outside number cannot go into the inside number, we're going to add a decimal point, and we're going to add a 0 down here. 4 does go into 10 2 times. 4 times 2 is 8. Now, we don't add these two numbers. Long division rule says once you did the 4 times 2, which is positive 8, we'll subtract them. 10 minus 8 is 2. Now, 4 cannot go into 2, so we're going to add another 0. Bring it down. 4 goes into 20 5 times evenly. And so our answer then is 0.25. And we read that a certain way. So let's talk about how that's read. Now, when we look at that, when we're taking a decimal and turning it into a fraction, we'd have to be able to read this. So when we read this as 25 hundredths. So let's write that, 25 hundredths. Now, once we've read it and we wrote it, now we want to reduce it. So what we have to think about when we are reducing is that we're going to reduce by a fraction of 1. Because if you multiply a number by 1, then it doesn't hurt it. If you divide a number by 1, it doesn't hurt it. So what we're going to do then is take this 25 hundredths and we're going to divide it by a fraction of 1. And so we have to think about what is the largest number that goes into both 25 and 100. Happens to be 25. Now you can do 5 2 times if you wanted to. It still works out. And then from there, what you're going to do is 25 divided by 25 is 1, and 100 divided by 25 is 4. So this way we can see how to change a decimal into a fraction. Now we'll do another one here. We're going to practice with 3/5. Again, we're going to take that 3, put it inside, and put that denominator on the outside. 5 cannot go into 3. We're going to add a decimal point and add a 0. 5 goes into 30 6 times. 5 times 6 is 30. And it ends. So we've changed it to 6/10. Now, sometimes in the textbook, you're going to see it like this. Now, why do they put that 0 out front? Well, they do it as a place value holder. Plus, they want to make sure that you see this decimal point, that it's not an accident that it's there. That decimal point is very important. Big difference between 6/10 and the number 6. Now, let's practice changing a number into a fraction. So here we have 2 and 35 hundredths. So I read it, now I'm going to write it, 2 and 35 hundredths. And what we need to do is we need to reduce this 35 hundredths. So I'm going to take it over here, and I'm going to think to myself, what's the largest number that goes into both 35 and 100? It's going to be 5. then I know that 35 divided by 5 is 7, and 100 divided by 5 is 20. So since 35 hundredths reduces to 7 twentieths, I'm going to change this, show the reduction as 2 and 7 twentieths. I want to make sure we bring that whole number 2 out in front because it's out there. It's a whole 2 plus another part. We want to make sure that it's tied together. Now repeaters use a bar. So how do we know how to change this into a fraction? Well, let's take a moment here and talk about what we were just saying about just regular decimals. If we were to look at this, we know that that is represented as 3/10. The difference is that this and this are not the same thing. And the reason they're not the same thing is because of that little bar. So we know that the numerator is going to be the same because it's a 3. But the denominator's got to be different because we've got to be able to show that little line. So I want you to think about that little line as a 1. And think about it this way. 10 take away 1 is 9. So I'm going to prove to you that this little method that I just showed you actually works. I'm going to take 3 and divide it by 9. Oops. Get a little carried away here. 9 goes into 30 3 times. It's 27. Do some subtraction. And we see that the 3 is repeating. And it's going to keep repeating. So this is going to be 0.3 repeating. Okay? So this actually works. But we have to remember that we've got to reduce it. We can't leave it as 3/9. So we're going to reduce the top and bottom by 3. And what that does give us is 1/3. Okay? We're going to do it again for this one, just to prove that it does work. Okay? Here, normally I would have said 45 hundredths, but because of the line that shows that it repeats 45, 45, 45, it's really 45 99ths. Now we need to reduce that. 9 goes into both numbers. "45 divided by 9 is 5, and 99 divided by 9 is 11. So it's going to be 5/11ths. Once again, I'm going to prove it to you that it does work. 11 goes into 50 4 times. Got to do some borrowing. 11 goes into 60 5 times. Once again, do some borrowing. And we can see that it's starting to repeat once again. So we know it's going to be 0.45 with a bar over it. So we did prove that this 5/11ths works. All right, let's do a couple problems again on your own, see how it works. Here we have 0.2 with a bar repeating. So we would normally say 2/10, not 2/10 because of the bar. The bar is telling us that this is going to keep going on and on and on. So we need a little bit more than 2/10. So it's going to be reflected as 2/9. Now, if you think about this a little bit, you'll know that it's got to be a little bit more because 0.22222 is larger than 0.2. So in the denominator rule, the bigger the denominator or the larger the denominator, the smaller the number. If this is large, then the number is small. Okay? So in other words, it's like a pizza that you would cut up, and you would cut up into even smaller pieces because this is going to be a little bit bigger. So if it's going to be bigger, that means I need bigger pieces. That means it's not going to get cut up as small. So you can kind of relate it a little bit that way as well. Okay, let's take this number, which is a fraction, 6/11ths, and let's change it. So 6 divided by 11. And 11 goes into 60 5 times. 55, and we're going to borrow and subtract. And we're going to keep going because it's not repeating yet. 11 goes into 50 4 times. We're going to borrow and subtract, and it starts to repeat. So there's that 6 that's repeating. So this is going to be 0.54 or 54/10, but it's repeating. Now I can prove this to you a little bit differently. Normally, if I was to go just take this, just like we did a moment ago, take this decimal and turn it into a fraction, I would have said 54/99. True? So what number goes into both 54 and 99? 9 does. So that way when I reduce it, I'm back to 6/11. So we can see that this all works. Now what I want you to do is I want you to watch something, and I want you to think about what we did the other day when we talked about perfect squares. Now, we were talking about the rational and the root sign. And in our discussion of perfect squares, we were saying that it takes a certain number to make a perfect square. For example, we used Cheez-Its. So when we did one Cheez-It, right, measured 1 by 1. When we built a 2 by 2, it made up a total of 4, right? 4 Cheez-Its, we can get a perfect square. We got that 2 by 2. We did the same thing here with the 3 by 3. And when we talked about it, we said, hey, this radical sign reflects being the side measurement of the square, the root of the square, because it is a square root. So the side measurement of this square of 1, an area of 1, would be 1. This would make up 4, an area of 4. So the side measurement of a square that has an area of 4 would be 2. The side measurement of a square with an area of 9 would be 3. Now, one thing we didn't talk about, though, is we didn't talk about the fact that it could be negative as well. Now, it could be negative because a negative times a negative is equal to a positive. So we can say that it could be -2 times -2 would give us 4. -3 times -3 would give us 9. But when we're actually doing real life measuring, we deal mostly with the principal square root. In other words, the positive one. Because when we do measurement's always recorded positively. So if we're actually doing some real world problem, we would only concern ourselves with the positive root, the principal square root. We would not concern ourselves with the negative square root. Okay? So let's take a look at this and see if we can do it. So in this problem, it says x squared equals 81. What is it telling us? It's saying, hey, there's a square and its area is equal to 81. Here's that square of 81. So what would the side measurements be? Well, if I wanted to find x, I just want to find one side. And we would use the square root to do that. Okay, because 1x, which would be only one side, because this is x times x, right? So one side then would be equal to 9. But we also know that it's possible it could be -9. If it was an actual measurement, we would stay just with the positive. Here in example 6, we have the square root of 36. So again, if we want to know the side measurement of a square that had 30 units of 36 as an area, our answers would be 6 and -6. Okay, I want you to watch a little bit more because we talked about cube roots as well. So as we were talking about cube roots, let's get that to go away. There it is. We're talking about in 3 dimensions. So now, instead of a square, which was a 2-dimensional and the side measurement of a square, for a cube root is the side measurement of a cube. All right, so we also built in class cubes, and I'm going to refer to this 2 by 2 by 2 cube that we had done. And when we had done a 2 by 2 by 2 cube, which was a length of 2 and a width of 2 and a height of 2, it ended up being 8 cubes. So 8 cubics was what we were using. So if we were to look at this, this is saying the side measurement of a cube that's 8 cubics, right? That's our units, right? Our area would be 2. Now, here's a question I have. Is there such a thing as a principal cube root? So, in other words, are there 2 roots available for this, for the cube root, and we only consider 1, or there's only 1? Well, let's think about this a second. I need to be able to multiply a number 3 times. 2 times 2 times 2. That's what gave me the 8. Can I multiply a negative number? Can I do -2 times -2 times -2? Will that also give me a positive number? No, it will not. That's going to be a negative number. So I wanted to get positive 8. So it's impossible to have a cube root, a principal cube root, excuse me. You can get a cube root, but it won't be a principal one because there's only one. Now remember, the same is true if you're talking about something just trying to get uh, a negative cube. So if I was talking about the cube root of -8, then the only cube root to that would be -2, because -2 times -2 times -2 is -8. So something to think about. So one last time, here we have x cubed equals 64. So they're wanting to know, if I had a cube, a three-dimensional cube, and I had that and I drew it here, which I'm not very good at drawing, but I'm going to do it. I'm going to draw that three-dimensional cube. Okay, and if I draw this three-dimensional cube and putting it together, let me get over here a little bit. Okay, how much longer is a side? How long is a side? So we have to think about it, that we are talking about the cube root of 64. That's what we're looking for. So think about our numbers. 2 to the third power, 2 times 2 times 2 is 8. 3 to the third power, 3 times 3 times 3 is 27. Escalates quickly, doesn't it? And 4 to the third power is 64. So that means each side, the length, the width, and the height, all measure 4. So x would equal 4. Hopefully this helps you to better understanding about rational and irrational numbers in terms of roots, decimals, and fractions.